Let me welcome you to this lecture. We have now seen the preparation of metal allyl complexes, and we have seen that there are essentially three major strategies that are used for preparation of allyl complexes. In the first strategy, we have seen that the metathesis reaction is carried out where allyl ligand or allyl group from a main group organometallic reagent replaces a labile ligand in a precursor complex, and in the second case we have seen that a sigma allyl complex can form a pi allyl complex via sigma pi rearrangement reaction. And then we have also seen how one can prepare allyl complexes starting from eta 2 as well as eta 4 metal olefin complexes. So the preparation of other enyl complexes, that is say for example preparation of pentadienyl complexes as well as cycloheptatrienyl complexes essentially follow similar strategies, and they can be prepared by methods which are similar to the ones that are adopted for preparation of metal allyl complexes. So now we will discuss about the bonding in metal allyl complexes, and then we'll also look at the reactivity of these metal allyl complexes. So if we want to discuss about the bonding in metal allyl complexes, we need to identify the orbitals on the allyl ligand as well as orbitals on the metal ligands which are going to interact with each other and then form metal allyl complexes. So in case of the allyl ligand, we know that there are three carbon atoms and these carbon atoms participate in pi bonding, and all of these carbon atoms have unhybridized p orbitals which essentially you get involved in pi bonding. So these three atomic orbitals, so p orbitals on the carbon atoms, form three molecular orbitals during formation of this allyl ligand. And these three molecular orbitals, one is the bonding molecular orbital, one is non-bonding, and the other one is anti-bonding molecular orbital. So let us draw these molecular orbitals on the allyl ligand, and then we can find out the respective metal orbitals which can go and participate with these molecular orbitals of the allyl ligand. So this is the bonding molecular orbital of the allyl ligand, where all the p orbitals on each of these carbon atom are in the same phase. Then we have the non-bonding molecular orbital, where two of the p orbitals are in the same phase while the third p orbital is in the opposite phase. Now this central p orbital or p orbital on the central carbon atom can be in phase either with this p orbital on this carbon atom as well as p orbital on this particular terminal carbon atom, and that is why we can choose not to draw this particular p orbital on the central carbon atom and instead draw only the two terminal p orbitals. Then we have the antibonding molecular orbital of the allyl ligand, where only three p orbitals are in opposite phases. So now let us label these three molecular orbitals: the bonding one as psi1, the non-bonding molecular orbital as psi2, and the antibonding molecular orbital as psi3. Now each of these carbon p orbitals in the unhybridized p orbitals on the carbon atoms carry 1 electrons, and that is why the total electrons that are available for pi bonding are 3, and that is if we fill these orbitals in the 3 molecular orbital, that is psi1, psi2 and psi3, then psi1 is going to be completely filled and psi2 is going to be occupied by only 1 electron. So now these molecular orbitals are going to interact with metal orbitals, and we can identify the metal orbitals which are going to interact with psi1, psi2 and psi3. So with psi1 we can easily identify that the s orbital on the metal will be able to interact with the psi1. And then we also can see that the p z orbital of the metal will be able to interact with the psi1, as well as the z square molecular orbital of the metal will be also of the right symmetry to interact with the psi1 molecular orbital. Then for psi2 molecular orbital, if we assume that the x-axis lies on the plane of the board again, and their axis also lies on the plane of the board, then we can figure out easily that the px atomic orbital on the metal will be able to interact with psi2, as well as the xz atomic orbital of the metal will have the right symmetry to interact with psi2 molecular orbital of the allyl ligand. And then we have the for psi3 we can figure out that py atomic orbital of the metal, as well as dyz that is the yz atomic orbital on the metal will be able to interact with psi3. Now, during interaction or during formation of these metal allyl complexes, all these three molecular orbitals are going to interact with different metal orbitals, and now because of these interactions, essentially, or these interactions creates a barrier of rotation around the, if we consider this to be the allyl ligand and this is the metal attached to the allyl ligand, then these interactions, all these three interactions of different molecular orbitals of the allyl ligand with respective atomic orbitals of the metal creates a barrier of rotation along the allyl metal bond axis, because if this bond cannot have difficulty to rotate, or because there is a barrier of rotation, because if the allyl ligand rotates, then these interactions or the will have to be ruptured, as uh, the, the, uh, the, the symmetry of the lobes of different orbitals which participate in these interactions will get mismatched if we start rotating the allyl ligand along this allyl ligand to metal bond axis. So because of that, there will be rupture of these interactions, and this essentially creates a barrier of rotation along this allyl ligand metal bond axis, and this barrier of rotation is visible in the proton NMR spectra of these metal allyl complexes. And what one essentially observes is that when one records the proton NMR spectra of these allyl complexes, these two hydrogen atoms attached to the terminal carbon atoms essentially will appear as non-equivalent hydrogen atoms, even though they are attached to the same carbon atom. Over here, they appear as non-equivalent, as this hydrogen atom, which is towards the metal center, can be labeled as or categorized as NP, and this hydrogen atom, which is away from the metal, can be categorized as syn hydrogen atom. So let's label these hydrogen atoms, which is NP, as H1, and which is syn as H2, and then let's label also the central hydrogen atom as H3 hydrogen atom. Now, in some of these metal allyl complexes, we do see that these terminal carbon atoms, terminal hydrogen atoms, so the syn hydrogen atom and the anti hydrogen atom are non-equivalent in the proton NMR spectra, and they show different peaks for in the proton NMR spectra. Each of these hydrogen atoms appear as different signals. But in some of these metal allyl complexes, what is observed is that these hydrogen atoms appear as equivalent hydrogen atom, and only one signal is observed for both of these two hydrogen atoms. So this means that there is an interconversion between the hydrogen atoms, and this interconversion mechanism is faster than the NMR time scale, and that is the reason why these hydrogen atoms can appear as one signal or as equivalent protons in the proton NMR spectra. So this can happen if there is a pi sigma pi interconversion between the in the allyl complexes of those kind where the hydrogen atoms appear as equivalent hydrogen atom, and so since this is a pi allyl complex, now a sigma allyl complex can form from this pi allyl complex, and if that happens, then this is the H3, this is H, and this is also the hydrogen. So again, these are hydrogen atoms on the terminal carbon atom on the other side. From this side, now this is a sigma allyl complex is formed from the pi allyl complex. We have earlier seen how one can make pi allyl complexes starting from sigma allyl complexes by the sigma pi rearrangement reaction. The reverse can also be is possible, and the sigma allyl complex can form, and in this way now this carbon metal bond over here is a single bond, and it is formed by sp3 hybridized low on the carbon atom with interaction with the respective atomic orbital of metal, and that is why this particular bond can now freely rotate, as there is no barrier of rotation for this particular bond, as well as the CC bond of this, this allied carbon atom, central carbon atom with this terminal carbon atom, which is attached to the metal center, is also can also freely rotate, as there is no barrier of rotation for this particular bond as well. So both of these two hydrogen atoms, which were earlier different or non-equivalent, now they lose their distinction, and they both are now equivalent in nature. Now when this allyl complex is reformed from the sigma allyl complex, it may form in such a way that this is H3 and H2 may become now empty hydrogen atom, while H1 may now become the seen hydrogen atom, what we have seen, which is opposite to what we have seen in case of the precursor over here, where H1 was in empty position while H2 was in seen position. The opposite is true in case of this one here, that is via this pi sigma pi rearrangement. While the pi allyl complex is reformed from this sigma allyl complex, these hydrogen atoms may switch their positions, and that allows one to and if this pi sigma pi rearrangement essentially is faster than the NMR time scale, or it happens faster than the at a time which is faster than which is shorter than the time period that is required to record the NMR spectra, or one scan of the NMR in the NMR spectrometer, then what is going to happen is that with these hydrogen atoms on the terminal carbon atoms will essentially appear as equivalent hydrogen atom, and they will not appear as two different signals, and instead we will see only one signal. Now such pi sigma pi interconversion can be triggered by the presence of a Lewis base, and this is obvious when we look at the proton NMR spectra of the palladium allyl complex, or dinuclear palladium allyl complex, that for the preparation of which we have seen earlier. So if you record the proton NMR spectra of this particular compound in CdCl3, what you are going to see is that this is say H1 and this is H2. So this is around delta ppm is NMR chemical shift, and this is 3 ppm, this is 4 ppm, and let's say this is 5 ppm. So H1 will appear as a doublet, and H2 will also appear as a doublet, the different signal, while H3 here will appear as a septet or heptet. So here is the H3. So that happens because these two hydrogen atoms are different, and each of these actually split the signal for H3, and that is why we see a heptade over here. And what we have is these two hydrogen atoms, or the hydrogen atoms on the terminal carbon atoms, essentially appear as separate signals, and they are non-equivalent in nature. But now this is the NMR spectra that one obtains in CbCl3 solvent, which is a non-nucleophilic solvent. And now if one records the NMR spectra of this same compound in DMSO medium, what happens is that one observes the only one signal for both H1 and H2, while the signal for H3 becomes a pentet. So, and the signal for H1 and H2 is a doublet because of coupling with H3, while the signal for H3 has become pentet because there are four equivalent hydrogen atoms now next to this the carbon atom that is the attached to the H3 atom. So this essentially tells us, and this NMR spectrum is recorded in DMSO, tells us that the hydrogen atoms, that is seen hydrogen atom and the anti-hydrogen atoms essentially are equivalent, and one records the NMR spectra in DMSO medium, and that happens because the pi sigma pi interconversion in this case is triggered by the nucleophilic solvent, which acts as a Lewis base here, and that allows one to see the protons as equivalent protons. So that is one of the interesting aspects of bonding in metal allyl complexes, and we will now discuss about the uh, reactivity of metal allyl complexes. And when we talk about the reactivity of metal allyl complexes, the cationic allyl complexes serve as very important synthetic tools in organometallic chemistry because of their highly electrophilic substrates, and it allows one to carry out a nucleophilic attack on olefins essentially, because olefins as such are not susceptible to undergo nucleophilic attack, and instead they undergo only electrophilic attack in all the reactions. But when the olefin is essentially coordinated to a metal center, and then one forms a cationic allyl complex from this metal olefin complex, then it is possible to carry out nucleophilic attack on the olefin carbon atom. So let's see one example here. So if we take this diolefin complex, we know that if we do electrophilic attack on such diolefin complex in presence of 2 electron donor ligand, then the ligand will get transformed into a allyl ligand, and the metal will also get coordinated to the 2 electron donor over here because of the unsaturation that one creates when the diolefin gets converted into a allyl complex, and this complex is going to be positively charged, and such cationic allyl complexes, or on such cationic allyl complexes, now nucleophilic addition can take place, or nucleophilic attack can take place on one of the terminal carbon atom, and this will essentially give us this product, because now, although the diolefin complex is first formed, but such diolefin complexes are unstable, and that is why the diolefin complex will undergo decomplexation reaction and instead produce the olefin here as the product, and the metal will essentially come out as a byproduct over here as a complex again. So this is how one can carry out nucleophilic attack on such metal cationic metal allyl complexes, and for non-cationic or for neutral metal allyl complexes, one can use a Lewis base again to make them cationic, and then one can carry out the nucleophilic attack on such complexes. So for example, if one takes the binuclear palladium allyl complex, from the synthesis of which we have seen that one can prepare binuclear palladium allyl complexes by reaction of olefin with PdCl4 2 negative in presence of a base. This gives us binuclear palladium allyl complex of this kind here. So we have this sort of binuclear metal allyl complexes. And now if we add a Lewis base, PPH3, it will replace these chlorides and a mononuclear complex will essentially be formed. That is so that is going to be cationic. And now nucleophilic attack can take place on such metal allyl complexes, cationic metal allyl complexes, and if we use dimethylamine as the nucleophile, now this will go and attack on one of the allyl carbon atom over here, and this will essentially produce in this way. So this is how one can carry out nucleophilic attack on such olefin substrates via formation of metal allyl complexes, and this essentially is possible because here palladium allyl cationic palladium allyl complex is formed. But since such the palladium metal is quite expensive in nature, and using palladium in stoichiometric quantities here to carry out nucleophilic attack on such olefins is going to be quite expensive a strategy, and that is why one needs to use palladium as in only catalytic quantities. And we'll see one example here where one can use palladium metal as a catalyst in catalytic quantities to carry out a nucleophilic substitution reaction in allyl acetates essentially. So if you take allyl acetates, so let's take it as X. X is nothing but acetate. Now if you use palladium diphenyl phosphine, so let's call it palladium L2. So it will undergo oxidative addition reaction with palladium diphenyl phosphine. So this diphenyl phosphine it is. L is nothing but diphenyl phosphine here. So palladium, once it reacts with this allyl acetate, it will undergo oxidative addition reaction and it will get oxidized into palladium plus 2 oxidation state here, while in the starting it was in palladium 0 oxidation state. So then, and it forms a sigma allyl complex in this way. So this is how a sigma palladium allyl complex is formed. Now this complex, so this is the first step of this reaction. In the second step, the sigma allyl complex will undergo sigma pi rearrangement reaction to give us a pi allyl complex, and then since the double bond will come and attack on the metal center, one of the group, that is the X, will get released from the complex, and this will essentially produce a cationic metal allyl complex, because where X is going to be the counter anion. Now, nucleophilic attack can take place on this cationic metal allyl complex, and nucleophile can come and attack on the allyl group, and that will essentially give us this sort of a product here, while the starting palladium complex will get regenerated in this state. So that is the third step of the reaction. So this is how one can use this palladium palladium catalyst, or palladium can catalyze such nucleophilic substitution reaction on allyl acetates via formation of these cationic metal allyl complexes. So one can obtain such, one can carry out such nucleophilic substitution reactions very easily by using palladium as the catalyst. So this brings us to the end of this lecture. What we have seen during this lecture are the kind of orbitals that the allyl ligand utilizes for formation of metal allyl complexes, and we have also seen the consequence of these interactions as it essentially creates a barrier of rotation around the allyl ligand metal bond axis, and that can be essentially, it is demonstrated in the proton NMR spectra of the metal allyl complexes, and in some of the cases the hydrogen atoms or the terminal carbon atoms do appear as equivalent, and that happens because of pi sigma pi interconversion, which is faster than the NMR time scale, and that is why the protons can now appear as equivalent protons. Then we discussed about uh, uh, the effect of Lewis bases on this pi sigma pi interconversion, as in we have seen that in some of these cases the Lewis bases can trigger such interconversion, and that is why such metal allyl complexes which has non-equivalent hydrogen terminal hydrogen atoms uh, in non-nucleophilic bases, essentially they become equivalent protons, or the interconversion becomes faster when one aids as a Lewis base like BMSO, say for example. Then we have looked at the reactivity of these metal allyl complexes, and we have seen that these cationic metal allyl complexes serve as a very important synthetic tool, and this allows one to carry out nucleophilic attack on such olefinic substrates, and essentially we have seen a couple of reactions where one can use this strategy to prepare different derivatives of olefins. And we have also seen that how palladium metal can catalyze such a nucleophilic substitution reaction via formation of cationic allyl species where nucleophilic attack can take place. So during the next lecture we will discuss more about the reactivity of such metal enyl complexes, and with this let me conclude this lecture, and I thank you very much for being with me during this lecture.